Good morning, dear students. My name is Farhan Mazher, and today is 22nd April 2022. Right now, I am with the 11th Cambridge class, and the subject we are studying is Cambridge O levels of physics. This is today we have selected a paper May June 2015 Physics 5054 41 paper. It is alternative to practical ATP paper. We call it paper 4. And this paper 4 belongs from the zone 2. The time allowed for this paper is 1 hour. So let's start this. So May June 2015, a 4-1 paper is showing up on your screen. So let's start today's paper. Okay. A student investigates a ball bouncing on a bench. So they are dropping a ball and it will bounce from a bench. So they are observing that. The student drops the ball from a height h of 100 centimeter above the bench, as shown in the figure 1.1a. So from a height of 100 centimeter, they will drop the ball. They are calling this height capital H. He measures the height h of the ball at the top of the first bounce. The motion of the ball is shown in the figure 1.1a, b, and c. So they drop the ball from a height of 100 centimeter. They call that height capital H. So when the ball takes the first bounce, that height is called, the height of that bounce is called small h. And they have shown here. So you see, you drop the ball from here, so it hit the bench and then it takes the bounce. So whatever is the height of that bounce, that is called small h. He says, state how the student can check that the meter rule is vertical. So if you want to, this meter rule is vertical. If you want to make sure that this is vertical to the bench, you have to make sure that this angle here is 90 degree. So the method is very simple. You can take a set square and place the set square here in such a way that the two sides of the set square, which are perpendicular to each other, one of them is coinciding with this vertical rule, and the other side is coinciding with is along with the bench. So this will make sure that the meter rule is vertical. Another method is by the plumb line. Plumb line, is a thread, and at the end of the thread, we have a metallic bob. So hang the plumb line along with this vertical meter rule and check if the distance of the thread and the vertical rule remains same throughout. That will mean that the vertical rule is exactly vertical to the bench. So let me show you my written answer, and then, okay, so here you can see that here it comes. Place a set square at the bottom of the rule like this. You see, I have shown the meter, the set square. In this figure, you can see here the set square have been placed here. Place a set square at the bottom of the rule. Sides of the set square perpendicular to each other. One side should be with the bench and the other with the rule. So the two sides which are perpendicular to each other, one of the sides should be with the bench and the other should be with the rule, and that will make sure that the rule is a vertical. Okay, so let's check the marking scheme. What the marking scheme has to say. It says use of the set square describe, use of the plumb line up with vertical object in room, use of spirit level with explanation. So we have given the first answer. Okay. Okay, so now the next question. He says state and explain which part of the ball the student should use when measuring the age. So you see, we will use the bottom of the ball because bottom of the ball touch the bench, and so That's why we will measure the height of the bounce from the bottom of the ball, because the bottom of the ball touched the bench. That's the reason. Okay, so let me show you my written answer, and here we go. H should be measured from bottom of the ball to the bench because the bottom of the ball hits the bench. That's the reason. So let's have a look at the marking scheme. What the marking scheme has to say: bottom of the ball and some explanation for the bottom of the ball hits the bench. And H measured from to bottom of the ball. And another very important thing is the capital H was measured from the bottom of the ball. Okay, so let's go to the next question. He says on the figure 1.1c, mark and label the H. And then he says on the figure 1.1c, draw the position of the student's eye when measuring H. Okay, so these are the two questions. So the H will be from here to the bench, small h, and the eye should be placed here. Exactly, the line of sight should be perpendicular to this scale, this level where from where you will measure the height. So let me show you. I have done this. Okay, so here you can see I have shown here, this is the small h, the height of the bounce, and the eye should be here. The line of sight must be perpendicular to the scale from where you will measure the height. So I think our answers are right. So let's go check the marking scheme, and the marking scheme says a line from the bench to the level with the bottom of the ball, and the eye drawn a level with the bottom of the ball. So our answers are right. Okay, so let's move to the next part. He says suggest two reasons why it is difficult for the student to measure H accurately. You see, we are measuring the height of a bounce. So because the ball is moving, the one reason is the ball is moving. The other reason is the ball stays at that height for a very short time. Another reason is the ball is bouncing, moving, and we have a vertical scale there, but there is a little distance between the ball and the moving ball and the vertical scale. So you have to kind of little make a guess how much height it has gained. You can see the ball is bouncing here, and the vertical scale is here from where you will measure its height. So there is a little gap between them. So that's why it's not possible to get very accurate reading. So these are some reasons. The ball is moving, that is the one reason, and the distance between the meter rule and the bouncing ball. So these are the two reasons which I have written. So let's check the marking scheme. He says any two correct answers. For example, ball is moving, ball not close to the ruler, difficult to drop and observe. To do the for one person to do this is difficult, that he drops the ball and he observes the height of the bounce. For a single person, it is difficult to do both the jobs. So bounce height varies and difficult to position eye at correct position. Okay. So because you have no idea how high it will go in the bounce. The the student repeats the experiment for different values, the different values of H. For each value of the capital H, he takes 3 readings of the small h, the height of the first bounce. He records his results in the figure 1.2. So from here, you can see when he dropped the ball from 100. So these were the heights of the first bounce. So you can take the average. So for each value of the H, the average value of the H is H average. And complete the figure 1.2, giving your values of the H average to 3 significant figures. So add these 3 values and then equals to, and then divide with 3. So repeat that procedure for all of them. So I have done this already. So let me show you. Here we go. So you can see on your screen that I have already done. I've added these 3 equals to divided by 3 equals to, and these 3 equals to divided by 3 equals to. So we have found the values of the H average, small h average, the height of the first bounce, their average values. And these are here in this situation, they dropped the ball from a height of 100 centimeter. Here they dropped the ball from a height of 90 centimeter. Here they dropped the ball from a height of 80 centimeter. Here they dropped the ball from 60 centimeter, and here they dropped the ball from a height of 40 centimeter. Here they dropped the ball from a height of 20 centimeter. So I hope our answers are right. Okay, so let's have a look at my reading. 66.7. So where are my ratings? 66.7 and 13.3, the last reading, 13.3. So our answers are almost, they are right. Okay. So let's move to the next part. He says, we are done with the first part. Okay, he says on the figure 1.3, plot a graph of H average in centimeters to the y-axis, the height of the first bounce that will come on the y-axis against the capital H in centimeters on the x-axis. That is the ball, that is the height of the ball, the height of the ball from where you dropped it. So start your axis from 0, 10. So the y-axis will start from 10 and the x-axis will start from the 0. So we will look at our table and we will do that. So let me show you, and here we go. So the first thing which you will do, you will label your, do the labeling. So on the x-axis, because this is the x-axis, so it's going from 20 to 100. So we started our x-axis from 0, 0, 20, 40, 60, 80, 100, 120. So this labeling is very important. On the x-axis, I'm representing the capital H, and that's in centimeters. On the y-axis, let me reduce. On the y-axis, we are representing the small h average, and that is also in centimeters. And you know the small h average value is maximum 66.7. So we have 10, 20, 30, 40, 50, 60, 70. Okay. So then I will plot these points. So at 100, it is 66.7. So I will plot this point. And at 90, it is 60.3. So I will point this. 60.3, I cannot plot. I will plot 60 and 61. Between that, I will put a dot. And then at 80, you have 54. So 54 here. So at 60, you have 40.3. 40.3 means 40 and 41 in the center of that. And then you have at 40, you have 26.7, which is approximately 27. So here we have put a dot here between 26 and 27. At 20, you have 13.3, which means 13 and 14 in the middle of that. At 20, you have 13 and 14, 13.3, which is between 13 and 14. Okay. So put that dot. And then he says on the figure 1 plot, draw the straight line of the best fit. So then I have, luckily these points were in the same line. So I just joined that. Sorry. And you have joined them with the line of the best fit. Whenever you draw a line of the best fit, your line must be in the same pattern as those points are. And you should make sure that if there are some points left on one side of the line, same number of the points should be left on the other side of the line. Here in this case, all of the points are in the same line. Okay. Then their question is, let me check the marking scheme, what the marking scheme has to say. Axis correct way round labeled quantity and unit, scales more than 1/2 grid, linear, not awkward, points plotted accurately within 1/2 small squares, best fit, straight line drawn. And one, okay, so that's the next part. Okay. The next part coming up, he says the quantity E is given by, the theory shows that E is constant. Using 2 points from the graph, calculate 2 values of E. Comment on whether E is constant for the student's results. So from our graph, I will take 2 values and I will check what is the value of the E by those 2 values. So here we go. So I have taken 2 points from this graph. From this graph, I'm going to take 2 points. One point I have taken is 60, 40, and other point I have taken 100, 67. So for each point, I will find out the value of the E. He has given us the formula for the E. He says H average divided by the H, and we have square root on both of them. So under root 40 divided by under root 60, that is 0.816, and E for the second point will be under root 67 divided by under root 100, and both these values, this gives you 0.81. So the actual value is 0.82, and both from both the points, the E value is same. So both values are very close to each other. So student result is confirmed. There he said E is a constant. So yeah, from our calculation also, it is constant. So one value calculated, two values calculated, and some comment. For example, values close, so relationship holds. Okay. So we are going to the next question. Okay. Here we go. The next question coming up on your screen. A rain gauge is used to measure the amount of rain that falls. Figure 2.1 shows a typical rain gauge. So here we have a rain gauge. You know, this is an instrument, rain gauge, which tells you how much it has rained, and it's in the shape of a cone. And this is a spike, and this is ground, and it is fixed in the ground, and it's vertical, and it's like a jug, but the jug is in the shape of a cone. So here you can see it can measure up to 5 millimeter, 10 millimeter, 15 millimeter, 20 millimeter, 25 millimeter, 30 millimeter. But the interesting thing, which you will observe, that this is made of plastic, it's transparent, and the water is collected during raining in this. And from here, I can read that how much it has rained. So you can see the readings of 0 to 5 millimeter, and they have large distance between its divisions. And from 0 to 5 to 10, the distance between the divisions has decreased. And from 10 to 15, he has not shown the 11, 12, 13, 14. Okay. So as you go up, the distance between the readings is decreasing. Okay, due to the shape of this. The shape of the rain gauge caused the scale to be non-linear. With reference to the figure 2.1, explain what is meant by a non-linear scale. The non-linear scale means that the distance between the deviance in this gauge is not uniform. The distance between the deviance or the markings or the readings is not constant. Here it is large distance, and as you move up, the distance between the readings decreases. So that's the meaning of the non-linear. Okay, so here we go. It says the distance between the readings on the scale is not uniform. So let's check the marking scheme. Distance between the deviance changes with the depth. Okay, so that's their answer. Okay, then they say suggest why this non-linear scale is useful in a rain gauge. So it can measure up to large volume of the rain. So suggest why this non-linear scale is useful in a rain gauge. Measure small amount of rain very accurately. It has larger range. It can measure when the rain will be in the less amount. It will measure it very accurately. But even in the case of a heavy rain, it has large range, so it can measure up to large amount of rain. Okay, so let's check the marking scheme. Measure small amount more accurately, larger range of the readings. Okay. So then he says, suggest why. We are done with B part. On one day, the rain gauge measures 7.5 millimeter of the rain. On the figure 2.1, show the level of the water in the rain gauge. Okay, so we have to show the level 7.5. So let me increase the size so I can show you. So I think this is not very clear. Okay, so this is 5, this is 6, this is 7, this is 8. Between the 7 and 8 will be 7.5. So I put a dotted line here and written here 7.5 millimeters. So that was their question. Okay, so then their question is, a student picks up the rain gauge to read it. Suggest one possible source of error. This cause in the reading the rain gauge. You see, when the student will pick the rain gauge from the ground, and there are chances that during that process, he might spill some water out of the rain gauge. So that is one possibility. The other one is when you are holding the rain gauge in your hand, there is possibility that you might not be able to keep the rain gauge vertical. Maybe a little bit tilt in the rain gauge, and then the reading will be obviously changed. So these can be some practical problems, and water might splash and spill over. That's my answer. So let's check. The water, okay, sensible command, for example, difficult to hold correctly, gauge may be tipped, rain sticks to the walls of the container. So some of the rainwater is still with the walls of the container. Okay, so these can be some problems. Okay, so let's move to the next part. He says, suggest a reason why the rain gauge is made from a transparent material and has a spike. You see, why it is made of the transparent material? So the scientist or whoever is going to observe the reading or measure the reading, they can see the water. So the material is transparent, so you can see the level of the water. And why does it has a spike? Spike means this. This is the spike. Why it has a spike? So that it can be put in the ground firmly. And during the rain, when it will be filled, it do not topple. So the spike is for the stability. Okay, so let's. So the level of the water can be seen, and while you have a spike, it remains stable in the ground. It will keep the rain gauge stable in the ground. Marking scheme. So you can see the water, hold it upright in the ground, more stable, stays in position. These are the answers. So let's move to the next question. The next question coming up on your screen is the question number 3. He says, a student determines the refractive index of the glass in a semicircular glass block. The student uses the relationship refractive index is equal to the sine of the angle of incidence divided by the sine of the angle of refraction. Describe an experiment the student can perform to obtain an accurate value for the refractive index of the glass. Normal laboratory equipment is available. In your description of the experiment, you should state the equipment used, describe how the equipment is used, state the readings taken, explain how the refractive index is obtained from the readings, describe how the student makes the experiment accurate. So the semicircular glass block is drawn for you in the figure 3.1. You may draw on the figure 3.1. So on the next page, we have this figure. This is the question. And it's a 5 marks question, question number 3. And here is the figure. So this is the semicircular glass block. Okay. So basically what we will do, we will take a white paper and we will fix the white paper on a drawing board. And let me show you. So what we will do, we will take a white paper and we will fix that white paper on a drawing board so that the white paper cannot move. Then I will put a semicircular glass block like here we have. And then I will mark its boundary of that semicircular glass block on the white paper with the help of the pencil. Once you have marked the boundary, then remove it, and where you have the straight edge of that semicircular glass block, on that straight edge on the paper where you have drawn its boundary, find its midpoint, and at that midpoint draw up normal, the dotted line which I've drawn, normal, and then put it back and place exactly over that dot on that boundary, and then take a ray box. The ray box is like a torch. It will give you the light. So shine that ray box, the torch, the light, or the laser towards the circular glass block. So this incident ray is coming and it will enter here along the normal to this circular glass block. So the light will not deviate and it will go to this middle point. So from here, the light will emerge because you are using light and you will be able to see that light. So you will see that the light will emerge from here. So on this incident ray, from where the light is passing, put two dots on the paper and name them as P1 and P2. Where the light is coming out on that ray, put two dots on the white paper and call them P3 and P4. Then remove everything. Join the P4 and the P3 up till it touch this point of emergence, and join the P1 and P2 with each other with the help of a scale and the ruler, scale and the pencil, and take this line straight to the this point. Okay, so then the check what is the angle between the incident ray and the normal here. That's the angle of incidence in the glass. And check what is the angle between, with the help of protector Meyer, what is the angle between the normal and the emergent ray. And I will call it the angle of refraction. I will call it R. Then you can find very easily the refractive index. The formula for the refractive index will be sine R divided by sine I. We always put that angle in upstairs, which has which is in the rare medium. Okay, so let me show you my written answer. He says, fix a white paper on the drawing board, place a semicircular glass block on paper, mark its boundary, take a ray box and direct its beam on curved surface such as shown in the figure. Mark 2 points P1 and P2 on the paper along the incident ray. Mark 2 points P3 and P4 on the emergent ray. From emergent ray, from plane face or a straight edge of the glass block, remove block and ray box, join P1 and P2 with the block up till straight edge. Join P3 and P4 with the straight edge of the glass block. Draw a normal at the point of emergence. Measure the angle of incidence and angle of refraction with help of a protector. Use the formula sine R divided by sine I to calculate the refractive index. Repeat by changing the angle of incidence. So you see that will give you more accuracy, and then take the average of the n value, the refractive index value. You see here in this formula, n is equal to sine R by sine I. Sine R means that the angle of refraction we put in the numerator here in this formula, because that's the rule. The angle which is formed in the rare medium is always in the numerator in this. So I hope you have understood this experiment. And so this is that experiment which is showing up on your screen. This is that whole question. Question number 3. Okay. So let's check the marking scheme first. Okay. A correct experiment described that must be refraction, ray box or pins, and protector and ruler, and anyone from plain paper, board, sharp pencils. Mark ray in air on both the sides of the block with the pins or crosses. Written description of the join points in air to block both sides, and remove the block to draw ray in the block. Correct angles measured and labeled on the diagram and described if no diagram drawn. Accuracy mark, for example, repeat, described anywhere, find pencil, pins, or part, bottom of the pins, large angles, vary angles of incidence. So this is the marking scheme of this question, and you can write a better answer than my answer. Okay, so we are going to the question number 4. He says the student measures the time for which a 1.5 volt cell can provide a steady current of 0.3 ampere. The student sets up a circuit including the cell. She measures the current produced by the cell and varies the resistance of the circuit to keep the current constant. In the space below, draw the circuit she uses. So let me show you. I have done that. Okay. So here you can see I have made that diagram, and you can see I have connected a battery, an ammeter, and a variable resistor. The resistance of this variable resistor or rheostat we can change. Then their question is, okay. Then he says, name the equipment the student uses to measure the current. To measure the current, we use ammeter. Vary the resistance. For that purpose, we use a variable resistor. And measure the time. For that purpose, we will use a stopwatch. Let me show you my written answer. So ammeter, variable resistor, and the stopwatch. Variable resistor is also called a rheostat. The student chooses from 3 analog meters to measure the current. The meters have a range from 0 to 10 ampere, 0 to 1 ampere, and 0 to zero point 0.1 ampere. Explain why 0 to 1 ampere meter is most suitable. Okay, so the current in your circuit is 0.3 ampere, and these are the 3 ammeters. So your current is 0.3 ampere. So you cannot use 0 to 10 ampere because 0 to 10 ampere will give a very small deflection for the 0.3 ampere. So you will not be able to notice it, or you can say the deflection in the pointer of the ammeter will be very small if you use the range of 0 to 10 ampere, because your current is only 0.3 ampere. You cannot use 0 to 0.1 ampere. The reason is the current which your circuit has is 0.3 ampere, which is out of its range. And the best will be 0 to 1 ampere, because 0 to 1 ampere will give a large deflection when the current will be 0.3 ampere. So we will use 0 to 1 ampere meter rule. Meter rule, I was supposed to say ammeter. Okay, so here you can see it will give a large deflection for 0.3 ampere current. Okay, so that's why we'll use from 0 to 1 ampere. Describe how the student adjusts the circuit to keep the current constant. When you will start your experiment, and for example, that you observe that the current is 0.3 ampere. Obviously, after some time, the current will start dropping. So when you see that the current is going down from 0.3 ampere, you will reduce the resistance of this variable resistor. And when you will reduce the resistance of this variable resistor, automatically the current will become stable. The current will increase again. Start with maximum resistance of the variable resistor, gradually decrease the resistance of the variable resistor. Okay. Then the question is, let me show you question. Then the question is, a second student repeats the experiment using a much larger current. Suggests one hazard in this may cause. If you use larger current, a very larger current in the circuit, due to the heating effect of the current, there is chances that the resistance might melt and blow, or your wiring will melt or blow. The connecting leads will melt. So let me show you my answer, and then we'll go. Rheostat might become very hot due to the large circuit. Rheostat is that variable resistor whose resistance we can change. It will become very hot if the current is large. So we are done with this paper. Okay. So that was the last question. Let's have a look at the marking scheme. It says correct circuit symbol for single cell ammeter variable resistors L3 in series. Ammeter, variable resistor, rheostat, potentiometer, stopwatch, and all three corrected. Of the scale of 0.1 ampere meter and 10 ampere scale, deflection too small. Reduce the resistance of the variable resistor as current decreases. Rheostat wire becomes hot. That's the B part. We have done that. So the wires might become very hot. Okay, so that was the B part. Do I have written this answer? Yeah, we have done. So, my dear students, today, my dear students, we have done May, June 2015 4-1 paper. This was paper 4. We call it alternative to practical. The time allowed was 1 hour. I have tried my best to explain you the concepts which were involved in this paper. I hope you have understood this. And this video, if you are watching this video have made your physics past paper practice little easier. So my dear students, if you find this video interesting, informative, and helpful to you, do share the link of this video onto your Facebook accounts, Instagram accounts, and the Twitter accounts, because that will help me promote my channel. And don't forget to like this video and also subscribe this channel. And thank you very much. It's a blessing for me to teach you and help you online through this medium of the YouTube. God bless you all.